Okay, welcome. First of all, the reason I'm doing this, I'm going to make these 4 short little videos here, or they're going to be about 5 minutes each. I figure I owe you at least 20 minutes, if not 25. Because here's the deal. This is how much you pay for the 3-hour lecture portion of this class. It's $1,018. We meet 29 times. Most of you have been pretty good about coming 29 times. That means it's $35. I should charge, I have to charge you for walking in the classroom. Did you get your 35 bucks a day? Hell no. All right, so here we go. Now, what I've done is I've worked up the problems here, and let's just look at problem 17, and I'll get you started on 18 real fast. Okay. Now, I tried to do the solution, the student view, so we could get it without answers, but it keeps going to a funky thing. All right, so now you can explore the concepts that are important in this problem if you go to that simulation on 10.3, which is okay. It's an okay simulation, but okay, a block of mass of 0.187 kilograms is fastened to an unrestrained horizontal spring. All right, and so here we go. Let's start. First of all, here's our block, 0.817 kilograms. Okay, it's attached to that spring. All right, I kind of drew that kind of small. So let's see if we can do make it a little bigger. There we go. That's a little better. All right, let's go back to what else it says. Okay, it's fastened to an unrestrained. Okay, K is equal to 81.6 newtons per meter. The block is given a displacement of 0.108 meters. Okay, I'm writing these down. K is equal to 81.6 newtons per meter. Because if you can do 17 and 18, you've got the gist of what we were supposed to do today. And as a bonus, I'm going to do problems 22 and 23 to show you I'm not a complete idiot. And I didn't have to look up the solution. All I had to do was just sit where I could actually think and not be, going, oh my God, they think you're an idiot. Yes, they do. All right. Anyway. Okay, so now we got the displacement. And then it's released from rest. Boing. Okay, so then that's where it's going to have its max acceleration and all of that. So I know that x is equal to 0.018. So let's show some of the things we already know. All right. Okay, so I know that this is the spring constant. Okay. All right. And I also know that when it's released, that omega is going to equal the square root of k over m. Ha! That's kind of cool. Do I have k? Yes. Do I have m? Yes. And a is equal to 0.018 meters. All right. So I think we've got everything we need here. All right. So let's take a look. So we pull it out. So what we do is we pull it like this. Okay, and it's going to have a restoring force going this way. All right, so its initial velocity, is going to be 0, but its A max is going to be negative, and that's going to be A omega squared. All right, where omega is equal to k over m. All right, and we've got A and we've got that. So, and V max will equal A times omega, and you've got k over m again. All right. So that gives you the framework for that problem. Let's see what else we needed to answer. What is the force? Okay, well, you know what F is, right? Let's just write down. Okay, so F is equal to kx. That'll be the initial restoring force. What do they want in B? Find the angular frequency. Oh, omega. What is the maximum speed and determine the maximum acceleration? All right, we wrote all those down. Good. So let's look at problem 18 next.